Hi everyone, welcome back. So myself Ayush Tripathi. Currently I am working as a mentor and a problem setter at GeeksforGeeks, and I welcome you all to this post analysis video of the last weekly contest 175, and the problems were easy to moderate level. The last problem and the second problem were based on some very standard problems. So let's just quickly start with the first problem, maximum product. In this problem, you are given an integer array ARR of length n and also given two integers L and R, where L is less than or equal to R, and you have to choose one element from the subarray starting from index L to R. Here L and R both are inclusive, and another element from the remaining array such that the product of these two elements should be maximum. And another important thing, one base indexing has been considered. So for this particular sample test case, the maximum product that you can make is 21. The value of L is 2 and the value of R is 4. So this is the subarray. From this subarray, select 7, and from the remaining array, select 3. So their product is 21. So let's see how we can solve this problem. So the very crucial observation, we always we just only need to keep track of the maximum and minimum element from the remaining array and from the subarray. So here, so there will be only 4 possible cases, and basically some other cases will be also there, but all the cases are being covered with these one. So let's say here this is the variable which I have used in my implementation to store the minimum element from the remaining array, and this variable will store the maximum element from the remaining array, and this variable I have used to store the minimum element of the subarray starting from index L to R, and this is stored the maximum element of the subarray. Cool. So what are the possible cases we can have? So the first case where all the elements are positive. So in this case, to get the maximum product, what you can do, you can select the maximum element from the remaining array and the maximum element from the subarray, and their product will give you the maximum result. Will give you the best answer. And what if all the elements of the subarray and remaining array are negative? So in this case, selecting the minimum element and from the remaining array and the minimum element from the subarray will give you the positive product. So this is the result. And then the third case where the remaining array is having positive elements and the subarray is having negative element, and vice versa. The same thing is true for the vice versa case where the remaining array will have the negative element and the subarray will have the positive element. So in this case, the product is always a negative number. Now we have to minimize this negative number. So for this thing, what I can do, I can just simply select I can just simply select the smallest positive number, that is the minimum from here, and then minimum, then maximum from here. Cool. To get the maximum product, that is least possible value, least negative value. Then this is the fourth case, and some other cases which has been indirectly covered from these four cases. So there might be a case when you have negative and positive both. So in such cases, you have to consider both the ways. So there might be a case when the product of negative, which going to be a positive number, is the maximum, or there might be a case when the product of positive numbers is maximum. So what I am trying to say, you have four values: subarray minimum, subarray maximum, remaining minimum, and remaining maximum. So just consider all the four options. Cool. So yeah, this is the complete implementation. Let me just show you the. This is the complete explanation. Let me just show you the implementation here. So this is the method that you have to complete, and here I have subtracted 1 from L and R just to convert it into a zero-based indexing. Then remaining minimum and remaining maximum, then subarray minimum and subarray maximum. Then iterate over all the elements, and if the current index is greater than or equal to L and less than or equal to R, then it is the part of the subarray. Then update subarray minimum and subarray maximum. Similarly, otherwise I will update remaining minimum and remaining maximum. And these were the four cases that we have to consider basically all the four possible pairs, and we'll select the best out of it. The time complexity is linear, extra space, no extra space such as array string or something. So that's why the extra space is constant. Cool. So this is the second problem of the contest, boundary sum of matrix. In this problem, you are given a matrix of size n cross n, and you have to find the sum of each level boundary in the matrix. So for this matrix, you have to first find the sum of outermost boundary cells, then second outermost, and so on. So this problem is a variation of the very standard problem, spirally traversing a matrix. And make sure to check out this problem. And basically there is very slight change. Instead of printing the boundary cell, now this time you have to compute their sum. Cool. So I will use the same technique, same standard technique, that is use four pointer variables. The first pointer variable is named as SR, that is a starting row, and then a starting column. Both has been initialized with 0, row 0 and column 0. Then end row and end column, again both initialized with n minus 1, as the size of the matrix is n cross n. So then in each iteration of the outer loop, and what is this outer loop? We'll discuss in the implementation part very soon. So in each iteration of this outer loop, I will process all the four boundaries, that is top row, right column, bottom row, and left column. Then in the second iteration of the outer loop, I will process the second boundary, second outermost boundary. Cool. So let's see how we can process the boundary rows and boundary column. So starting from the top row, basically I'm using the same idea, that is spiral order traverser. First I will traverse over the top row, then right column, then bottom row, and then left column. Cool. So for the top row, what I can do, I can just simply start iterating from j is equal to SC, that is the starting column, from where we have to start, and it goes till end column, EC. Cool. And then I will add the value of cell A of SR, that is a starting row, since it is a top row. So a starting row, and then current column. So I iterate over the columns and then starting row. Cool. And after this, what I will do, I will just simply increment the value of SR, that is SR plus plus. Since I have processed the top row, so that's why we simply increment it, that is take me to the next row. Cool. And then I will process the right column. So for this thing, what I can do, I can just simply start iterating from top row to the end row, that is from start row to the end row. So I is equal to start row, and then it goes till ER, and then I will add A of current row, that is I, and the column is EC, that is end column. Cool. So basically I'm iterating over these elements from SR to ER, and the column is EC. Cool, makes sense. And after this, I will just simply decrement the value of EC, that is take me to the previous column, since I have processed the rightmost column. Cool. So EC minus minus this column, and then I will just simply process the row, bottom row, which is these many cells starting from 9 to 3. And for this, I can just simply write a logic, that is start iterating from j is equal to EC end column, and it goes till SC, the starting column. Cool. And then sum plus equal to A of ER, that is end row, because it is the bottom row. So end row of the current boundary, and the column number is simply j. And after this, I will just simply decrement the value of end row, that is ER minus minus. Makes sense. That is take me to the previous row. Next, bottommost row, this one. And for the left column, so how I can process the left column, and for the left column, I can just start iterating from I is equal to end row. Here I'm printing from bottom to top. You can also start iterating from start to end. It's totally up to you. That is the start row to end row, but I'm using the spiral order traversal logic. So ER to SR, and then sum plus equal to A of ith row, and then the column is SC. Cool. That is the left column. And after this, I will just simply increment the value of SC. SC plus plus. Cool. SC plus plus. So this is these very iterations in the outermost loop. So in the first iteration of the outermost loop, I have processed all the four boundaries. That is this sum, and then I will just simply add this sum in a vector in my answer vector. In the next iteration, I will process this boundary. Cool. All the boundary lines of this current boundary. So yeah, this was the complete explanation. Let me show you the implementation here. So this is the method that you have to complete. So okay, instead of discussing over here, let me just discuss the solution from this editor itself. So this is my answer vector, and then count, and because how many times this outer loop will run, the number of elements that we have, you can also write some other logic. It's totally up to you. But the number of elements that I have is n cross n. So once I have added the sum of all cells of the matrix, then I will just simply terminate the loop. Otherwise, you can also come up with some kind of other checks and write it over this inside this while loop condition. Then SR, SC, ER, and EC. Cool. So initializing the sum with 0 for the current boundary. Then this is for a top row and SR plus plus. Then right column EC minus minus, and then bottom row ER minus minus, and then left column SC plus plus, and then adding this sum in a answer vector. Cool. So let's try to submit this. The time complexity is same, n cross n, and successfully submitted. So this is the third problem of the contest. You are given two types of drink, A and B, n rings of type A and n rings of type B, and you can drink at most y classes of drink A, and at most x classes of drink A, and at most y classes of drink B to maximize your health. But there is some constraint. The very first constraint, you have to drink classes from left to right from each row, that is from index 0 to n minus 1. And if you started to drink a glass of type B, then you can't drink a glass of type A. And for each index, you can either choose A. If glass of type B has not been chosen yet, or drink B of I, or you are also allowed to skip the current index. And obviously, the initial health will be 0. So let's see how we can solve this problem. So consider this example where the value of x is 2 and the value of y is also 2. That is at most 2 glasses of drink of type A and at most 2 glasses of drink of type B. So what we can do, we can select this one and basically one glass of type A, and once we have selected any glass of type B, then we won't be allowed to select a glass of type A anymore. That is some prefix of A and then suffix of B. So then we can select this 5 and 4. Cool. So can I say this thing? Basically, this is the complete solution. That is for each index I will select at most X best element, or basically the glass with the maximum value from the subarray 0 to I minus 1, and at most Y classes from the suffix with the best values or the maximum values from the suffix, that is from index B of I to B of n minus 1, that is this subarray I to n minus 1, and from the prefix I will select a glass of type A, that is from A0 to A of I minus 1. And if I do this thing for all the indices, then I can find the best answer. Cool. So for this thing, what I can do to select the best X classes from the prefix, what I can use a priority queue. This is a very standard problem. Priority queue. Cool. That is inside my priority queue, I will push the element, and once the size of the priority queue, I will declare this as a min priority queue, or you can also say as min heap. So what I will do, I will push the elements whenever I get the element value greater than 0, that is non-zero, because at here we have the term at most. You are also allowed to do not select any class. So that's why at most. So if I got the element which are having value greater than 0, that is non-zero, then I will push the element in the priority queue and add the value in my sum variable. And once the size of the priority queue is greater than x, because we were allowed to drink at most x glasses, then I will simply remove the minimum element of this priority queue and subtract its value from a sum variable. Cool. And for a prefix, I will do the pre-computation for each index I. So first I will iterate from I is equal to 0 to n minus 1, and then I will do the pre-computation, that is PA of I will simply store at most x best elements from the subarray 0 to I minus 1. And once I get this thing, then I can just simply start iterating from right to left for a class of type B, for a class of type B. And let's say this is the current index I. So from here I will select at most y best element. And to select at most y best element, what I can do, I can use the same logic of a priority queue. Once the size of the priority queue becomes greater than y, then I will remove the smallest element and subtract its value from a sum. Cool. And basically p a of I, that is this prefix from 0 to I minus 1, at most x classes from 0 to I minus 1, and from the suffix, that is I to n minus 1, I will select at most y classes and x classes from this prefix. Cool. So this is the complete solution, and it's take a linear time and the extra space because of this PA array. The space complexity will also be linear. So yeah, let me just show you the implementation. So here I have my PA array of size n plus 1, because 0 to I minus 1, then a sum variable, the best sum that we have so far, and make sure to use a long variable to avoid overflow cases. Then this is simply min heap. Then I iterate over all the indices from 0 to n minus 1 for the pre-computation. And if the element value is greater than 0, then only I will add in a priority queue, because we have to find the sum. And if it is negative, then it's best to do not include the element. So pq dot push a of I and adding its value in a sum variable. And once the size of the priority queue becomes greater than x, because at most x, then I will remove the smallest element, which is pq dot top. And actually the time complexity will be n log of n base 2, because here we are taking we are using the priority queue, which add the factor of log of n base 2, because adding the element takes a logarithmic time in case of heap. Then removing the smallest element, and pa of I plus 1 is simply equal to sum. Cool. Then removing all the elements from the priority queue from the min heap, because I'm going to use the same min heap for the suffix part, and updating the value of sum as 0. Then this is my answer variable, and I am initializing this one with PA of n, because there might be a case when the best answer comes from the class of type A. I will only select the classes from type A and at most x classes. Then iterating over all the indices from n minus 1 to 0, and if the element value is greater than 0, then only I will consider this element in the suffix. Adding this element in the priority queue, adding their sum in a sum variable, and adding their value in the sum variable. And if the size becomes greater than y, then removing the smallest element from the suffix and subtracting its value, and then taking this as my answer. Cool. Updating the answer, so that is answer is equal to maximum of answer that we have so far, and PA of I, that is at most x best element from the prefix 0 to I minus 1, and at most y element from the suffix, that is I to n minus 1, which is stored in this variable sum. Cool. And then I am simply returning this sum. Let me just quickly again repeat the time complexity. So the time complexity is n log of n, because of the priority queue, and the space complexity is also going to be linear auxiliary space complexity, because of this PA vector and this priority queue. Cool. So let's just try to submit this. So successfully submitted. So this is the last problem of the contest, longest increasing path in tree. In this problem, you are given a tree with n nodes and n minus 1 edges. You are also given an array values where values of I represent the value on ith node, and you have to find the length of longest strictly increasing path in the tree. And here one base indexing has been considered. So for this particular tree, the longest strictly increasing path start from node with the number 2, then 1, and then 3. As 2 is having value 3, then 4, and then 5, strictly increasing. So let's see how we can solve this problem. So this problem is a variation of very standard problem of binary tree, which is maximum path sum. So make sure to check that problem after this video. So we can break down this problem into three cases. The first case where the current node, let's say which is 6, is in the best path. So the best path starts from 5. Here I have written the node values instead of node numbers. So 5, 6, 10, and 12, strictly increasing. Then the second case where the current node, here also it is 6, is in the is the root of best path. So the best path starts from 5, node with the value 5, then 6, and then 7. So here 6, which is our current node, is the root of the best path. Then the third case where the current node is not in the best path. So the best path starts from 2, 4, and 6, and let's say the current node is 5. So the 5 is not in the best path. So we can easily solve this third case by using a variable to store the answer, update the answer every time. So I already have the answer. I already know the length of longest strictly increasing path, so which was 3. Cool. And whenever I get some better result, then I will update this answer. So case 3 is can be easily solved by using a temporary variable or basically answer variable. Cool. Let's see how we can solve case 2. So both the cases we can combine together, and the another observation, the path could be either strictly increasing or strictly decreasing. What I'm trying to say, let's say the current node is having value 10, then we can also merge this node 10. We can include this node 10 in the path of strictly increasing sequence, or we can also include this node in the path of strictly decreasing sequence. So what I'm trying to say, let's say there is some node which are having value greater than 10, then another node greater than 10, then in this way. So here we can start our path, best path from node 10. Cool. And it also starts from it could also be a decreasing order. Let's say the current node is having value 10, then let's say some node value, let me write some numbers here. Instead of a 10, let's say we have next node 8, then 7, and then some other node. So now in this case we can start our best path from 10. So it could be either strictly increasing or strictly decreasing, and these were the only two possible cases. So let me explain you with this example. So here we just only have to check for two cases. So the first case for strictly decreasing, strictly decreasing, cool, and the second case is strictly increasing, strictly increasing. So let's say the current node is having value 10, and let's say some child is having value 8. So we can start, we can make a path, and starting with the smallest node, and let's say 6 is the child of 8 and 4 is the child of 6. So we can consider this as a decreasing path. Starting from the current node, we ask that what is the length of longest decreasing path, because I can start from the smallest node. So let's say some child of 10 is having value 8, then 8 is having a child 6, then 6 is having child 4. So we can start our best path from node 4. Similarly, let's say some child of node 10 is having value 12, then we interested in the increasing path, and we simply start from this node 10 itself. We can start from this node 10 itself. Cool. And then the second case, let me write for the second case. The second case where the current node is in the path of, is the root of the best path. So in that case, what we can do, we can check for a increasing path and one increasing, and one decreasing. Cool. So from this side, from this side, we are interested in decreasing path. So let's say value 8, then value 6, and let's say then the value 4. So this 8 is a direct child of 10. So from this 8, I can just simply ask, tell me the length of longest decreasing path from you. And then I can merge this with the increasing path. So let's say some child of 10 is having value 12. Then from this 12, I can just simply ask, tell me the length of longest increasing path from you. So from this 12, let's say 12 is having some child of 15, then some child 18, and then some child 20. So now this node 10, this is a strictly decreasing path, strictly increasing, not decreasing. So now we can combine decreasing path and increasing path together by considering the current node. This is the current node 10 as the root node. This is a current node, and if this is a root node, we can say this is the path which starts from 4 and it goes till 20. So for every node, I need two information. For every node, I need two information. The increasing, that is what is the length of longest increasing path starting from you, and then decreasing, what is the length of longest decreasing path starting from you, because that might be contribute in the answer for the upcoming parents node. So we simply write our DFS function and visit all the child, and for every child we are checking, I will check the values, and if the value is less than the current node, then I will check for a decreasing path, and if the value is greater than the current node, then I will check for increasing path. Cool. So I guess this was all about the explanation part. Let me just show you the implementation. So this is the given function. So here I have just created a tree adjacency list, and then the longest path, that is my answer, is 1. I will initialize this answer with 1 because at least one answer is always possible. And then calling this function starting from node 1, which is the root node, and then its parent -1. We have to consider one base indexing. Then there's a adjacency list and the values array, and then there's a temporary variable, this answer variable longest path, to solve the third case where the current node is not in the path of is not in the best path. So I always update the answer, and I will return two information, strictly increasing and strictly decreasing, to the parent function. So this is the DFS function, and the return type is pair. And here I have a variable increasing and variable decreasing, both has been initialized with 0, and then current increasing and current decreasing for the current child, and then iterate over all its child. And if the child is not equal to parent, a very standard DFS, if the child is not equal to parent, then I will make a DFS call. And once I return from this DFS call, this p dot first is my current increasing, that is starting from the child node. What is the maximum length of increasing path? Similarly, what is the maximum length of decreasing path starting from the child node? And if the child node, that is values of u minus 1, because it is given as per the zero based indexing. So if the current node is having value greater than its child, then this is the second case when the current node, where the current node is the root. So if the current node is the root, then I can merge one increasing and one decreasing. So so this is increasing, and the best increasing that I have, then this is a decreasing, and plus 1 for the current node. Cool. And I always update the answer. I always interested in maximum decreasing length. So what I'm trying to say, yeah, this case. So there might be a case when some other decreasing path are also there. So let's say this 10 is having node of, is having some child as value with value 9, and then its child with value 7. So this is also a valid path. This is also a path, but we are not interested in this path, as we are interested in the longest strictly increasing path. So instead of considering this, we always keep track of the length of longest decreasing path. Cool. So that's why Here I am updating this variable decreasing. And if the node value is less than the child, then we are interested in an increasing path. So this is the second case, current increasing. This is the current increasing, and what is the best decreasing path that we have? As I can combine together these two together with the current root node and plus one for the current root node. And since it is an increasing path, so that's why I will update the increasing variable. Cool. And after this, what I will return to the parent function, I will just simply return increasing plus one because of the current node, and comma decreasing plus one, because this is the case one where the current node is in the best path, not the root. So yeah, this is the complete implementation, and the time complexity is linear as we are visiting each and every node exactly one time. So let me just quickly try to submit this. All right, so successfully submitted. So this was all about the last weekly contest. Thank you so much guys for watching this video, and have a good day.